All right, in our last video, we saw that aldehydes and ketones can react with primary amines to form an imine, where you have a carbon-nitrogen double bond. And we said it's a little bit different if you have a secondary amine. If you have a secondary amine react with an aldehyde or a ketone, you get what is called an enamine, where you get a carbon-carbon double bond rather than a carbon-nitrogen double bond. Like we said, the mechanism is similar up until about this step right here. This step is what differentiates enamines from imines. We said that we typically get the enamine formed because this intermediate, where nitrogen has a positive charge, is so unstable it'll quickly do kind of like an elimination reaction in order to get a new carbon-carbon double bond. All right, so let's do a few practice problems before we get too much further, and then we'll see some variations of these as well. All right, so the first practice problem is with this starting material. And if we were to try to name this, we could number the longest carbon backbone. And this would just be 3-pentanone. I did look up the IUPAC rules, and I guess they're getting a little persnickety now. I guess the IUPAC preferred name is now pentan-3-one. They like it now if you put that number before the suffix rather than in front of the parent. So I guess this one underneath is preferred. This one on top is what a lot of chemists would do. So I'm not going to be picky about which one you use. All right. Either way, you can react this with something like diethylamine, where you have two ethyl groups attached to one nitrogen. I'll just write that as Et2NH. And we can again imagine that this is going to be treated with acid under buffered conditions. And when I look at this, the first thing I immediately do is I say, well, this is a secondary amine, which means if we're trying to predict what our product should be, secondary amines will always give you an enamine, meaning we should get a carbon-carbon double bond, not a carbon-nitrogen double bond. So the question is, well, will it occur on this side that I've highlighted in yellow, or will it occur on this side that I've highlighted in green, or does it matter? In this case, I would say it doesn't matter at all because it's symmetric, right? The ethyl group off of one side of the ketone is the same as the ethyl group coming off the other side. So in this case, I'm not going to worry about that. However, I did want to kind of bring your attention to one thing. So we could get a double bond there, right? So that's the position that I recently highlighted. And we could end up with two different ethyl groups coming off this nitrogen. Let me kind of clarify that a bit. So those are my ethyl groups coming off the nitrogen. So when I look at that double bond, we could ask ourselves, well, is this an E or a Z double bond? Well, in this case, it looks to me like I've drawn a Z alkene in that position. The truth is you can get a mixture. So when we look at this, we could also get the diastereomer, where this double bond could also be an E. So then the question is, which one's major and which one's minor? Well, it kind of depends on a lot of variables. It depends a lot on sterics. Typically, you want to avoid the steric interaction. So it's not always going to favor E. It's not going to be Z. You want to ask yourself which one minimizes that steric clash. All right. So if you remember this reaction gives you a mixture of diastereomers, you'll be in really good shape. All right, let's take a look at some other nucleophiles that are kind of variations on nitrogen nucleophiles. All right, the first one I wanted to go over is kind of neat. If we have a ketone or an aldehyde, we can react it with a molecule that is essentially 1/2 amine and then 1/2 alcohol. This reagent is called hydroxylamine. And if we think about it, right, we've got a lone pair coming off of the nitrogen, And we also have lone pairs coming off of the oxygen. So the question is, well, what's going to act as the nucleophile? Will the nitrogen act as the nucleophile? Or will the lone pairs coming off of the oxygen act as the nucleophile? In this case, it's really important to consider electronegativity. Which atom prefers to hold its lone pairs more tightly? I would say that oxygen, because it's more electronegative, is going to be more greedy about keeping its lone pairs, right? Nitrogen, because it's less nucleophilic, is going to be more nucleophilic. So I'll just make a note here that this is more nucleophilic. And just like with the other reactions, we can treat this with our acid under buffered conditions. And if we think about it, hydroxylamine is still a primary amine. So if we ask ourselves, what would we expect to get out of this reaction? We know that primary amines tend to form that imine, where we get a carbon-nitrogen double bond. And that's exactly what we get out. So we get this compound right here, where it has the carbon-nitrogen double bond, and we also kick off water. However, we name this intermediate right here something even more specific than an imine. Specifically, what we call this is an oxamine. It's an imine that has an oxygen coming off of it, specifically an alcohol or a hydroxy group. This is a really powerful intermediate in organic chemistry. We'll talk more about this later, but for right now, I just wanted to introduce this new naming system. All right, the next one, in my opinion, is even cooler, where you can have a ketone or an aldehyde. Doesn't really matter. But this time, you're going to react it with something that is essentially a diamine. This is called hydrazine. And the question is, well, which nitrogen's lone pair will react? In this case, doesn't really matter, right? It's still a primary amine, though, on either side. And we could have this react with our catalytic acid. And again, if we predict what we'll get out, we'd say, well, it's a primary amine. So just like above, we would expect to get an imine, meaning we'd get that carbon-nitrogen double bond. So what we would anticipate getting is something that looks like this, where we'd have a carbon-nitrogen double bond, but now we'd have an NH2 kind of hanging off, and we'd kick off water in the process. This is a cool intermediate called a hydrozone. Again, it's a really powerful intermediate to have. All right, so what I want to show you on the next page is kind of a derivative of this hydrozone. So if you have a hydrozone, what you can do is you can treat this with KOH, potassium hydroxide, in water and heat it for a while. That's what that delta symbol means. And when you're done, you can completely remove that nitrogen group. So in a weird way of thinking about it, you can go from a ketone and get rid of that CO double bond and go straight to an sp3 hybridized carbon in the center. It's kind of neat. All right, so let's take a look at that reaction in a lot more detail. This reaction is called the Wolff-Kishner reduction. All right, so the Wolff-Kishner reduction is named after the chemist that investigated this. And I'm going to make my page a little bit bigger. And the mechanism's kind of interesting, but let's first look at the overall reaction. And in the overall reaction, you can have a ketone or an aldehyde. You can react it with hydrazine. And like I said, we need some sort of acid catalyst, but not too powerful. We don't want to protonate all of our amine. And I'm going to make this a one-way arrow, and we can favor formation of our product by removing water. And like I said, you can get this intermediate that's kind of like an imine, but we like to call it a hydrozone. So I'm just going to label that as a hydrozone. It's just being more specific. And if we have our hydrozone, We can then treat it with KOH and water and heat it up for a while. And when we're done, we can completely remove that group, and our byproduct is going to be nitrogen gas. So that nitrogen gas is just going to bubble out of solution. All right, so let's take a look at this mechanism in more detail. All right, so I'm just going to jump ahead straight to our hydrozone because we've already done the imine reaction a fair amount in our last video. And this would be our hydrozone after that first step. All right, in the next step though, the Wolff-Kishner reduction, we've got hydroxide and water around, right? So hydroxide is a pretty good base. The question is, well, where's the most acidic proton? I would argue that the most acidic proton would have to be one of these protons coming off of the nitrogen, right? We know that protons that are attached to electronegative atoms tend to be more acidic according to our cardio rules. So this will grab that proton, and what you can do is you can show your conjugate base where that nitrogen has a negative charge, right? So this makes sense. Nitrogen is a lot more electronegative than carbon. It's happier holding that negative charge than a carbon otherwise would be. All right. In this next step, though, it's important to think about the resonance. So the resonance structure basically says that we can kick electrons all the way down and share them with this lower carbon. So let's show both resonance structures. All right, that means that the nitrogen isn't the only atom carrying the negative charge, the carbon is as well. All right, so at this point, we've got this intermediate, and we've got water floating around, and water can act as a weak acid. So it's essentially going to act as a proton source for this carbon right here. So we're almost there. We've added that hydrogen in. However, we still have more hydroxide floating around. So if we have hydroxide floating around, you can imagine that we'll just do this one more time. So what happens is this will grab that proton, it will clamp down, we'll form a nitrogen-nitrogen triple bond. That's really what's going to form our nitrogen gas, and then we'll kick electrons onto this carbon underneath. Oops. All right, so that leaves us with a lone pair on that top carbon. We also have our nitrogen gas that will bubble out of solution. It's a really, really good leaving group. And then in our last step, all we need to do is protonate the position on the top in order to give us our neutral product. All right, so some people ask, well, why is this considered a reduction reaction? Well, if you actually figure out the oxidation number for carbon, you can see that it's gaining electrons through this reaction. So that's why it's called a reduction reaction. It's not that you're reducing it to an alcohol or an amine or anything like that. You're reducing it because you're gaining electrons there. All right. So let's take a look at this and compare it to some other reactions that we've seen. All right, and we've seen a reaction where we do something similar. In particular, if you have acetophenone, we saw that we could do that Clemmensen reduction, where you have a zinc amalgam, meaning it's zinc and mercury, and hydrochloric acid, and we could accomplish something similar, right? We could get rid of an aromatic ketone and just turn it into an aromatic molecule with some sort of alkyl group coming off of it. All right, let's compare that to the one we just saw. All right, this one underneath can do the same reaction, but this time I'm going to treat it with our hydrazine. I'm going to treat it with my acid. Let me make this arrow a little bit bigger. And I'm going to remove water from the reaction. Step 1 is to make that hydrozone intermediate. And then step 2 is to treat it with potassium hydroxide, water, and heat. That's the Wolff-Kishner reduction. In either situation, we get the same product. So then the question is, well, why would we do one over the other? We'll talk more about the pros and cons of each of these reactions later, but for right now, let's just leave it as is, and then we'll come back and look at the pros and cons for these various reduction reactions later. All right, so before we continue on, what I want to do is I want to look at a handful of practice problems from the book. And I know these look really overwhelming, so let's just break it down into the easy chunks. So let's zoom in on this first problem. And what I like to do is look at the product. So over here we've got this product. And then what I do is I ask myself, is this an enamine or an imine? Well, in this case, we've got an alkene, meaning a carbon-carbon double bond. So this indicates that it must be an enamine. We know that imines are formed when we have a carbon-nitrogen double bond, and we don't have that here. We have a carbon-carbon double bond. Furthermore, we know that enamines are formed anytime you have a secondary amine reacting with a ketone or an aldehyde. So that gives us a clue. So let's go ahead and look at the other half. In this portion right here, we probably want to put our amine. And then over here, we want to put our ketone or our aldehyde. All right, so the question is, what would the amine look like? Let's try to do that smaller box first. Well, looking at our product, it makes sense that what I've circled in orange must be the amine, right? So let's go ahead and draw that. If we have just that, we're not quite done. We need to have a hydrogen right there. So if we look at this, this amine is secondary. It would give us an enamine if it reacted with a ketone or aldehyde. So that seems to be fitting all of the major criteria. All right, that means that this portion right here must be the ketone or aldehyde that goes in that box. So we know it must have some sort of six-membered ring in it. All right, I'll show you another trick too. And that trick is identify the carbon that is bonded to nitrogen that is also participating in some sort of pi bond. So in this example, this carbon right here that I've highlighted and marked in red, well, I'll just mark it really big in red. That's the carbon that's bonded to nitrogen, and it's also participating in a pi bond. That carbon that I've marked in red must have been a CO double bond at some point. So if we go ahead and we look at this red carbon that I marked right here must have had a CO double bond. So in this case, it makes sense that we had a ketone as our starting material. All right, so let's do the same thing with the next one, and we'll break it down just like we did here. When I look at this product, I would say that it's an enamine. Again, we have an alkene. We don't have a carbon-nitrogen double bond. And again, that indicates that we must have some sort of secondary amine. All right, but this time, if you notice, there's no empty box for an amine here. So the question is, well, what exactly is occurring? But that's okay, let's troubleshoot it, right? Let's identify the carbon that used to have the CO double bond. And like I said up above, it's the carbon that's bonded to nitrogen that's also participating in a pi bond. All right, so if I look at this, we've got this carbon that's bonded to nitrogen, this carbon that's bonded to nitrogen, and this carbon that's bonded to nitrogen. Well, this one right here isn't participating in a pi bond, so I'm going to rule that out. Same thing with this one, not participating in a pi bond, so I'll rule that out. But this one that's remaining, Ah, that one's participating in a pi bond. So we must have had a CO double bond there. So let's go ahead and draw this in. And we know that 6-membered ring has this red carbon, must have had a CO double bond right there. And this methyl group underneath is probably going to stay put. And then we can go ahead. Let's see, 1, 2, 3. And we can draw it like this, where we can see that at this point, this portion is the amine, and it actually reacts with itself to form a new 6-membered ring. So it's a little bit weird, but you can imagine that this highlighted bond right here used to be a CO double bond, but now it's being formed between that nitrogen. All right, same idea up here. This highlighted bond right here is the newly formed bond, and previously that red position that I've marked up must have been a CO double bond. So these are a little bit tricky. All right, let's try one last one. This time when I look at it, I don't see a carbon-carbon double bond, I see a carbon-nitrogen double bond. So that means that I must have an imine. And again, that means that it must have a primary amine. All right, there's no box for a primary amine, which means something else must be going on. But let's do the same problem solving. Let's identify the carbon bonded to nitrogen. We've got 2 of them. And then ask ourselves which of those carbons is participating in a pi bond. It's not that one, so it must be that one right there. So this must be the position where the CO double bond used to be. All right, so let's go ahead and draw it out over here. So that ring has that red carbon there, and it must have had a CO double bond before. And down here, we must have an NH2 floating around, so this would be our primary amine. So this chunk right here is going to be the primary amine right there. So really what we're forming in this reaction is going to be that new double bond right there. So I know a lot of these require a lot of work. However, the more practice you do, specifically from textbook practice problems, the easier it is to start spotting some of these trends. So I would encourage you to spend a fair amount of time working on your skill builders for this chapter. It'll make it a lot easier and less overwhelming later on. All right, good luck studying.